All right, let's switch from graphics to physics this time around. So welcome. I'm gonna be talking a little bit about art and science of game physics. What we will cover today is gonna be how we approached multiplayer physics at Fingersoft, or at least a couple of our projects use this kind of solutions. And why we ended up building a custom solution for the physics part of the simulation. And I'll also cover some implementation overview and some videos of the results that we got. So first of all, I'm Teemu Väisänen. I'm the game development technical director at Fingersoft. And quick intro about Fingersoft. We are a mobile games company. We have offices in Oulu and Helsinki at the moment, and I guess we are probably best known from the Hill Climb Racing series games. So we have Hill Climb Racing 1 and Hill Climb Racing 2. Those two games have a combined 2 billion installs at the moment, so quite a few installs at the moment. And we're actually celebrating the 10th year anniversary this year, so big year for us. And of course, since this is the game shop fair, we are also hiring at the moment. So. All right, so that was the quick introduction how our games look, and as you saw, it was quite physics heavy, lots of stuff happening, lots of vehicles being affected by physics. So I would say that physics in general are quite. It's almost the core of most of our games. So, and another thing that we have is that physics has to also feel fantastic, no matter what the game is. And we don't necessarily care too much about the realism of the physics, and I would say that it's enough that it feels plausible in the game and how you feel it. And I would say that it has to just feel right, and that's what we are aiming for, rather than trying to do everything in a realistic fashion. So many of our current games or upcoming games are gonna be a little bit more geared towards the multiplayer part. And as you probably might know, physics and multiplayer are kind of difficult to do well. There's these inherent issues that we have when you actually try to combine those two. So here I tried a little bit like split the issue, at least one of the issues. This is just one part of the difficulty. But if you think about physics update, how it works, you usually have this. System has to run in discrete steps, so one after another, and of course you kind of rely on the previous result before you can actually calculate the next result. So it has to be going from one step to the second and then the third and so on. And I think all of the physics engines don't really like if you, for example, directly change a transform of a rigid body object. So basically there's a chance that, for example, you put the object inside of another collider, or you somehow violate a constraint that the object was constrained by. And then if you actually look at the network update side, you have the case where packets are arriving to the game. So these are usually, for example, changing the transform of the object. There's always a latency between the sending and receiving the package, and the packets may arrive out of order, or they might be completely missing. So, and you often have the case where the network update is actually changing the object transform directly. So if you actually compare these two, you notice that they are almost opposite of each other. There's no almost complete mismatch between the two. So basically, the other one wants to run in discrete steps, but the other one, there's a latency and the packets may arrive in whatever order. You have to handle those. And then other one wants to do everything through simulation, but the other one kind of tries to basically snap the object to a certain position. And what actually usually happens. Okay. Sorry about that. What usually happens in this case when you have a network update, for example, coming, and it directly changes the physics rigid body, you easily have this case where the physics basically explodes. So all the stuff that was once a whole becomes like huge mess. And of course, this will ruin your game if this is relevant to the gameplay, and player's card might be flying away in random direction. And these are really difficult to predict beforehand. So this is what we wanted to kind of avoid, and why we ended up in the solutions that we did. I actually had multiple slides about this, but I had to kind of dumb it down a little bit due to time constraints. But I tried to kind of split the options. Of course, you have option to not do any client-side simulation, and I would say that this is the kind of the optimal path that you should take if you can actually choose this one. Basically, the idea is that you don't actually do any simulation or stepping on the client side at all. So I would say that this is the best option if the game allows it. There is not going to be any sudden transforms to the simulation, but the big issue with this is that, of course, it introduces input lag to the player. So basically, you would probably send an input to the server or whatever authority you have on the other end, and then the server or one thing basically does the simulation, and then it sends it back to the client. So you have this inherent latency coming from that option. But of course, this is not a solution for any kind of fast games, and fast here means almost any kind of real-time type of game. And then the second option is to do some kind of a client-side simulation. Of course, there are like multiple variations to this, and I'm not going to actually go over the details of this in much of a detail. So, but as a quite typical example, you usually have a client that tries to somehow predict what's happening in the simulation before the server actually handles its like ground truth version. So you basically do some kind of a prediction to the physics, and then you send the input to the server, and then the server does its own simulation on its end, and then it sends back the result of that to the client, and then the client has to somehow go back in time to the original input that the server actually was handling, and then you have to do some kind of a re-simulation. So this is, for example, a good example when you would do some kind of a physics stepping in the background. But there are multiple options to this, and many cases when you want to actually run physics in a networked environment. But the rest of the slide is going to assume that we are handling some kind of a variation of the latter case of this. So we are making quite a bit of racing games, so I think this is a good example of the difficulties that you actually might face. I would say that the racing games are particularly difficult case for physics and multiplayer. The bodies basically move fast. Of course, the full server-side physics option is not an option for a racing game. It's almost impossible to drive if you have so much input lag coming. And often vehicles are quite complex to actually set up. So you have bodies, and then bodies are connected with quite complex joint systems together. For example, the springs, and maybe you have some like secondary motion on the vehicle, for example. And yeah, there can be lots of stuff happening even if you have a 2D game like these examples. So these are from HCR2, and also artists usually want to have some kind of a secondary motions to the, for example, if you look at the Moonlander over there, it has the antenna, so that they probably wanted to kind of flop around when you drive, so it feels like more like physical object rather than just some kind of a stiff thing that kind of floats around. So those kind of things are quite typical. Okay, so now what? What do we do if we have some kind of a case like this? Well, what we ended up doing was to kind of split the simulation into two parts, and then we do the partial network synchronization to the only one part of the equation. So how we split this into two was that we still have the gameplay physics side running. So this basically means any typical existing physics engine that you might have. It could be PhysX, it could be Box2D, it could be Havok, whatever you want to use. Basically, this covers the physical bodies that are relevant to the gameplay. And we kind of try to have this as simple as possible, because we know that if something can explode and break, it's much easier to kind of keep everything together if it's a simple case that we are covering. As a vehicle game or racing game example, you, for example, have the chassis and tires only affected by this system, and we actually do a full sync over the network for these bodies, or this side of the physics simulation. And then the new part is going to be the visual only physics. And the idea here is that we kind of only simulate the visual elements on this side of things. So this would be all the flappy stuff that you saw. So for example, the antennas and the camera was on top of the moonlander and stuff like that. So that kind of things. And this is going to be completely separated from the actual real physics. So it's a completely decoupled from that one. And what it means is that there's no way that the visual part of the simulation can explode the gameplay physics side of things. And that's the goal that we actually wanted to achieve originally. And these are usually for things that, for example, the secondary motion, and these are usually kind of the feels good or gameplay Jewish part of the physics. And we don't do any network syncing for these bodies. So it simplifies the setup quite a bit, and it actually saves quite a bit of bandwidth as well. So this is the example without any, or this would be the gameplay part of the physics. So it's quite stiff. The vehicle is still reacting to its movement, but there's no secondary motion at all here. So this is the left side of the previous slide. And then if we add the secondary motion, we actually get quite a bit of these like flappy bits. The hood is moving, the character is feeling much more alive. Everything is kind of feeling like it's an actual physical object that we're actually handling here. So this is all going to be run through the visual only physics side of things. So, and that's the separation that we want to do. So yeah, feels quite a bit more alive in my opinion, at least. Ooh, okay. So custom physics engine, it might feel a little bit like daunting at first, but it's actually not as difficult as it might sound at first. So, and we ended up using this algorithm or method called position-based dynamics. And we chose this because it's conceptually very simple to actually implement. And I would say that you don't need any physics or math degree to kind of get started. It's super simple concept, and the bit that I personally like most is that the constraints are super intuitive to actually implement. You don't need to think about, for example, impulses or forces or whatever that you usually have to do. This is just you're only thinking about the position of a point. But this is not like end-it-all solution. It might not fit you for some cases. For example, the algorithm itself is inherently serial, so you have to do things in a very serial manner to actually do this. But it also means that this is a little bit more difficult to actually multi-thread if you want to do that kind of things. It's possible to multi-thread this, but it means that if you have a very complex setup, let's say, for example, a cloth or something like that, where you have multiple constraints and points in the same system at the same time, then you run into the troubles with the multi-threading. But if you have small change of constraints, for example, then you can just put those into their own threads if you want. And this actually runs in GPU as well if you use, for example, compute shaders or something like that. So implementation, what did we actually do? We ended up actually building a custom package for any of our future and current Unity projects. And as I mentioned, it's going to be using the position-based dynamics. And the idea there is, again, that the real physics side of things doesn't know anything what's happening on the PBD side. And how things are ordered, this is stepping right after the real physics step is done. And you have to somehow still link things together. So how we ended up doing is that all the visual bodies or visual simulation is connected to the actual real physics bodies using fixed constraints. So if you, for example, have a vehicle chassis, then you have some secondary motion, then you just have a fixed constraint that attaches the visual body to that, and then you kind of follow the movement of the real body physics. And important bit about PBD is that how the velocity is calculated. And this is why this is actually super simple to implement to any other physics solution, is that the velocity is calculated using the previous step's position, and then you figure out what's the velocity of a point or mass. And it also means that velocity is not directly tracked at all. The real bodies can move freely, and then the Verlet just kind of automatically picks up the velocity without any extra work. You don't have to think about it at all on the PBD side of things. And then about the shapes, you usually want to have some kind of multiple types of shapes in your game. So we actually only support points for this system. But it doesn't mean that you, for example, couldn't do a box or more complex shape, because you can always form more complex shapes by constraining multiple points using distant constraints. So that's always an option. But it's also possible to do actual more complex shapes if you want. So how does the stepping work? This is a little bit dumbed down and not actual proper code, but maybe you'll get the idea. And I would say, first of all, step 1 and step 3 are actually kind of very much linked together, and you don't actually have to track the velocity there. But it was a little bit clearer if I write it down like that. So basically, first step is to move the particles. You have some kind of particle that has a position, so you add the velocity, and then you take the delta time into account there. But also in the step 1, you also add any external forces that the system may have. So usually this means gravity, wind, or whatever kind of global effect you want to have in the system. And then comes the constraints step. And this is the part that I like personally very much. You don't have to think about velocities, you don't have to think about forces, you don't have to think about anything complex. You're only considering the position of the particle, and if the constraint is violated, or if it's actually in a valid state or not. And I think the distance constraint is a good example of this. I have an example over there where two particles are too far away from the distance constraint, and the distance constraint wants the particles to be certain distance away from each other. You don't have to do anything other than just move the particles to the correct position until the distance constraint is satisfied, and that's it. That's all you have to do basically. And well, okay, you would probably take mass also into account in this example, but if all the points have the same mass, then you can just directly move them to the correct position. And then you do the update velocity step. And as I mentioned, this is only using the particle's previous position and then the current position, and you get the velocity of the particle, which you use again in the step 1. And that's how the simulation basically runs. It's simple. It feels like, is that it? But it actually works quite nicely. So here's a quick setup. I just added a few example kind of constraints. So there's the chain. It's basically just a few distance constraints linked together, and then there's this kind of hinge type of things that are distance constraint, 2 particles constrained together, and then there's also this hinge constraint, and then there's kind of a limitation to how much the angle can be. Or there's a constraint to the angle of the hinge constraint as well. So, and these are only a few lines of code. So probably altogether this is like probably less than 10 lines of code to implement this. But you can actually do more with this. So you could use it for characters. So this is a little bit more like a Ractal kind of case. I only added those constraints to the arms, as you can see. So I can move it freely. It picks up the velocities automatically. I don't do anything else. It just works. Everything works by following what's happening to the position of the system. And this was also super quick to kind of set up. It's just a few distance constraints and angle constraint, and I guess that's it. But yeah, if you're interested about the details, Matthias Müller is the original author of the method, and he has this excellent project called 10-minute physics, and he basically explains how the PBD works. And he also have a few examples of the kind of improved version of this. So there's a method called XPBD, which is kind of an extension to this, and it solves some issues that the original paper has. For example, the constraints become infinitely stiff, even though if you have if you don't want it to be stiff, but if you have multiple steps running, it actually approaches always to be infinitely stiff. But the extended version fixes that. But I would say that the original PBD paper works quite nicely for any game already. So yeah, I would say that we originally started that with the issue that from the multiplayer point of view, but we actually noticed that this kind of system has multiple other benefits as well. So for example, as you saw, the HR2 and HR1, they are 2D physics games. But you could, for example, add a 3D element to those. So you are not limited to just X and Y kind of transformations, because the gameplay could still be running in 2D, but it's quite easy to implement like 3D movement to the system using this kind of thing. And this is great for 2.5D games. And another benefit that we noticed is that this can actually be used quite easily for inverse kinematics system as well, because you can basically attach things of a character or whatever you want to kind of be under the IK system to a position. So for example, we had the driving example. I had this arms that were basically just attached to the wheel of the vehicle, and it works out of the box. But you can also, or the PBD has this concept of soft constraints. So if you use those, you actually get the feeling that you have some kind of a character that is kind of struggling to keep a position instead of like holding it like perfectly still on the target. So you get this kind of like human-like behavior if you loosen a little bit of the stiffness of the constraints. In general, I think the main benefit is still that this makes the physics setup quite a bit simpler. You only have a few constraints and bodies into the actual gameplay physics side of things. So, and even though I mentioned the explosions on the multiplayer concept, multiplayer side of things, it of course happens also in the single player games. So this kind of setup also can reduce those cases as well. So basically the idea is that if you have fewer bodies in the gameplay physics side, you have less transforms to sync, and then you have much more chance to things to break. And yeah, this is not restricted to multiplayer. What else? Okay, conclusions. Yeah, I would say that physics and multiplayer don't match. It's extremely difficult issue to kind of try to fix all the cases. And this is not an end-all solution to any multiplayer game, but this is small part of the equation that you might want to kind of consider. And next, I would say that you probably want to simplify the network objects in general, not only because of the physics side of things, but of course you want to kind of reduce for example, the bandwidth of the game that it requires to update everything. And at least we found the splitting of visuals and the gameplay as from the physics side of things, it was quite nice solution, and it had its own extra benefits, which was nice in our case. And if you want to approach your game quite similarly, then I would say that the BBD is actually a great option for this kind of visual simulation. Of course, you could use any physics engine, or you could perhaps even use the same engine and kind of split things up differently if you want it. But we like the extra benefits, for example, the 3D movement that we could introduce to our 2D game. So that was nice extra. And the actual implementation of BBD, it was like you can probably get started in one evening if you actually want to implement something like this. Of course, most of the work is going to be mostly about like making tools for artists and stuff like that. So that may take a little bit longer, but the actual implementation should be pretty quick. So yeah, thank you. That was it. And quickly, we are also hiring. Those are the positions that we have open. So thank you.
We have an interesting question from the online audience, so let me first ask it. How did you manage the floating point error when simulating a server and comparing the results with the client prediction?
We don't actually have to care about that kind of things, because the visual side of things is just kind of, it's completely separated, so we don't care about that kind of thing. So I think that's more about the issue on the how do you run the gameplay physics side of things. So yeah, basically it's a different issue than we are covering here.
We have a question from the junior. What would you recommend for a junior to learn more about multiplayer development and finding the best practices in the industry?
Multiplayer development. Probably start with some kind of like existing solution. I would say that, for example, Photon is pretty good example if you're on Unity platform, or perhaps the Mirror is quite good, at least that I've heard of. We are using actually custom multiplayer transport layer, for example. But I would say that if you're starting out, then it might be a good idea to kind of understand the basic concepts first, using some kind of existing, perhaps commercial solution before you dive deeper into the actual, like how packets are transferred and stuff like that.
Do we have questions from the audience? Then at what stage do the designers and artists get to test the results of their creation process?
Sorry, I missed it. Can you repeat?
At what stage do designers and artists get to test the results of this in their creation process?
Currently, at least so far, this is actually the setup part is done by the programmers at the moment. But we have a plan to kind of make better tools for the artists, so it's much easier to kind of do the setup process yourself and then just go into the game and try it out. So that's the end goal, but we are not there at the moment. So,
questions more from the audience? I think can take. Then I'm going to ask, it's not related to this, if I may. Okay. I know that your original game was developed in C++, and my first job was a C++ developer, so I know how hard it is. But my interest is that the new games you are developing with C#, maybe you can say why?
Well, there are multiple reasons. I would say that, for example, the engine that we use for ATR1 and ATR2, it's kind of maybe aging a little bit at this point. it's not the most modern solution available. So in that regard, it makes sense to concentrate on a little bit more modern engine like Unity or perhaps Godot or stuff like that. But of course, big part of that equation is that it's much more easy to find talents for Unity at the moment than it is for C++ developers. So that's a big part of the thing. And I would also say that Unity is excellent for any artist. There's quite a bit of existing tools and editors for almost doing almost any kind of game. So that's of course a huge plus for us. If you compare it, for example, to the Coco Studio, which is basically, for example, if you want to implement or add a sprite, that also requires coders' help. So you can imagine that the artists don't necessarily like a system like that.
Okay, I think that we have to wrap up. Let me check. Yeah, I think we covered. Anyone here want to ask the question? Otherwise, I want to thank you very much, Teemu, for being with us.
All right.
I think excellent presentation. And we're going to have actually all the recordings also available. So also for the people here on site, if you missed it, the recordings will be there.
All right.
Thank you very much.
Cool. Thanks.